8, 7, 6.
Oh, it was very exciting. It's the only one I've ever seen. It was at 12:30 in the morning, so it was dark. And my daughter, who was older, was awake and knew what was going on. My son was actually asleep, and we woke him up just to see the launch.
Booster ignition and liftoff of Columbia, reaching new heights for women in X-ray astronomy.
When I stood there 3+ miles away at the viewing stand and the shuttle engines lit up, and you could hear the roar, and my shirt was vibrating.
Most of the people who'd come down to watch the launch, that was it. We launched, everything was great. For us, of course, it was a very, very big step because now Chandra was off into space. But until we saw X-rays coming through and knew that everything worked, we couldn't really be too overconfident or relaxed or assured of success.
Nothing as beautiful as Chandra sailing off on its way to work.
I felt ecstatic. I felt unbelievably ecstatic. And when we saw those first X-rays at the first time the door opened, and I could see that they were being focused more or less into the right size area, I just broke into the biggest smile you've ever seen.
And we looked at Cassiopeia A, a supernova remnant of a star that exploded about 300 years ago. It's the neutron star, the core of the star that exploded, collapses and forms a neutron star. And we made that discovery in this official first light image as well. We were very excited.
That was an extraordinary time. I think when I first realized the telescope was working, I had a real sense of relief, a real sense of elation because of all the hard work that had gone on. I was incredibly proud because of the team and being part of that team.
So the requirement was that it had to work for 3 years and the goal was 5.
We're 15 years into our 5-year lifetime. That's not too bad.
So many people have contributed much of their careers to the success of the Chandra mission, and we're just to continue to reap the benefits of those sacrifices that they made and the excellent science return that we're seeing from the mission, and we hope those continue for years to come.
If you want to find black holes, you want to use an X-ray telescope.
From various astronomical observatories in space and on the ground, and in particular Chandra being a major player, we've determined that most galaxies that are as massive as our Milky Way or more have what we call a supermassive black hole in the center of the galaxy. Supermassive means that they weigh in at anywhere from 1 million to 10 billion times the mass of our own sun.
What we're tending to find is that a cluster of galaxies has a bright central galaxy in the middle. It's often an active galaxy or a quasar. So a supermassive black hole in the middle of a big galaxy. Because when the cluster is forming, a lot of the material tends to fall to the middle, so you get the biggest galaxy in the middle. You have cool material falling in, forming stars. Eventually some of that gets to the black hole. The black hole can't take it all in, so some of it's blown out in radio jets. That heats up the material that's coming back down. So there's a kind of feedback loop between the growing black hole in the middle and the star formation that's happening in the cluster itself.
We've known about the existence of dark matter for a long time. It used to be called missing matter, but now it's just dark matter because we know it's there. We know this in a number of different ways. So Chandra's discovery of some things like the bullet cluster is not a great surprise, but this is a situation, one of these train wrecks that you can see, and you can see that these galaxies collided with each other, and what's happened is very interesting and shows the presence of dark matter in a beautiful way.
What we've now seen is that when there is two clusters which pass through each other and the gas got stripped out and the dark matter kept going, and so they've actually enabled us in really the only opportunity in the universe that at least I'm aware of to clearly separate the existence of the dark matter, which then you can detect by this thing called gravitational lens effect, and the gas. And so this is like a key scientific discovery to understand the nature of dark matter versus normal matter in the universe.
And that's a very beautiful image. For me, it's beautiful because it combines together data from Chandra, Hubble Space Telescope, as well as the Magellan Telescope, a very powerful ground-based telescope. And it really, for me, shows how Chandra's science can be powerful in multi-wavelength space.
Important discoveries in astronomy and astrophysics was the discovery of dark energy, and that is that the universe is accelerating apart. What people are trying to do using various different techniques, and again in all the different wavelength bands, is to measure the parameters to characterize the dark energy. Chandra and X-ray astronomy is playing an important role in these measurements. Well, the universe evolves differently. It's not the universe we're in without it. I think that's most important. And secondly, if we're ever going to try to understand cosmology, that is the growth and evolution of the universe, these are important constraints, boundary conditions that have to be satisfied by any model that you may have.
I usually make the mistake of saying dark energy didn't exist at the time that we designed Chandra. Well, of course it's existed. We didn't know of the existence of dark energy when we designed Chandra. So you see the power of an observatory. An observatory like Chandra with a state-of-the-art telescope and these imaging and spectroscopic capabilities of its science instruments can do things that maybe weren't even things that you planned on doing because you didn't know about them at the time. And a lot of the science with Chandra falls in that category.
Yeah, the universe is a big, big place. I think in this mature phase, what we can do, which would have been harder to do in the early years, when you want to look at a lot of different things and satisfy a lot of observers, is taking really longer exposures.
Chandra has very sharp vision, but if you don't look for very long, you don't capture very many photons. And so you can't really populate that digital image with much detail. But if we stare at one region for a really long time, we gather so many photons that we can really understand the subtleties. We can see thousands of stars. We can understand how they change with time. We can look at the full zoo of denizens in star-forming regions. We're in the middle of a 2 million second observation with Chandra of something called 30 Doradus, the Tarantula Nebula. We've only got 1 million seconds so far. We see hundreds of stars. Some of them are very unusual and look like they're interacting binaries. We see strange, diffuse shock emission that we don't even understand yet. Another thing we can do with Chandra is to look wider, so we can start mapping regions that are degrees across on the sky, very complex fields. And we've done this once already with something called the Great Nebula in Carina. We mapped the Carina star-forming complex. From that we found over 14,000 young stars, and we find a distributed population of young stars as well as these dense clusters. And we also see an amazing array of diffuse X-ray emission.
If we look at them in the optical, what we see is a lot of galaxies. It's very pretty. If we look in the X-rays, we see the hot gas, which is actually much more of the material in the cluster, about 10 times more than the material that's in the galaxies. And that surrounds all those galaxies.
So many people that have been important to this success, continued success of Chandra. Obviously, at the head of the list goes Riccardo Giacconi. He conceived of this need for this observatory 9 months after he discovered the first X-ray source, Scobrius X1. He discovered that in 1962, so that was in 1963. You have to mention Leon van Spabroek, the Chandra telescope scientist whose brilliance and understanding of X-ray optics was such an important factor in being able to build this telescope and coming up with techniques how to do it that weren't going to break the bank and yet solve the problems that we encountered. When we started Chandra, we did not know how to build it. We knew the science we wanted to do. This was a purely science-driven program.
Chandra X-ray Center has a very strong team that works very well as a team. Biggest amount of credit for building that team goes to our recently retired director, Harvey Tannenbaum, who was really maybe the mother of Chandra all the way along, shepherded it through the original process to get it approved, etc., and built the X-ray Center team.
So it was incredibly well built. It was designed with very robust and reliable parts. The science instruments were basically new, and the telescope was certainly state of the art. We tested the heck out of things in the lab before delivering. We tested at Marshall during the calibration. There was testing during the full-up integration. There were some problems, there were some issues. We fixed everything we could find. I think we had, again, from a team perspective, we had great leadership at Marshall and throughout all of the contractors and the science team involved.
So by all of these metrics, Chandra is one of the most productive missions that there have been scientifically, and we're working extremely hard to maintain those levels.
Looking at all the components in detail, their condition now versus their condition at launch versus projections as to how long they can last up there, and there have been no showstoppers came up in that study, and all the things that the engineering team could be doing to mitigate aging are already being done.
Flight ops team and the science ops team, they continue to work together to really maximize our science while maintaining and protecting the health and safety of the vehicle.
We do have an extraordinary team, and they've worked together since the beginning of the mission and right through development before that. It includes the ground control team, the science center, the flight operations team, the science instrument teams, the factory support from Northrop Grumman, and our colleagues at Marshall Space Flight Center.
The quality of the science with Chandra, I think the legacy will be that it was really serious science. It was in there toe-to-toe with all the other branches of astronomy and astrophysics pushing the envelope.
Everything we look at is high drama in space, and it's a lot of fun.
Well, I think Chandra's legacy will be profound. Huge archive of Chandra observations continues to be used, and new things come out of it. The cleverness of the scientific community can't be underrated. People are smart and they have ideas, and they run the range from studying the interaction of exoplanets with their nearby stars and that influence on the planets themselves, an interesting topic of its own, to what is out there in the deep fields. We're going to increase the amount of observing time, and I anticipate that depending on the outcome of that, we may go even deeper. You never know what you're going to see if you haven't seen it before. I mean, this is the same thing that I said before launch. I said, I can tell you about 25 things that this observatory is going to do that are absolutely fantastic science, and they will be dwarfed by the 25 things that I couldn't tell you about, because if I could tell you about them, then my name would be Ricardo Giacconi or somebody like him, and I would be sitting somewhere else with my Nobel Prize. I think it's proven confidence that Chandra will continue to make outstanding discoveries because it's so unique.